Hello. So today I'm going to introduce one new topic. So far we have studied what is a probability on a probability space, and we have studied properties of the probability function, and we have also studied what is a conditional probability and Bayes theorem. So let us quickly recall that whenever we talk about probability, there is an underlying random experiment. The set of outcomes of that random experiment, we denoted it by S, and then the second component represents another set which consists of some subsets of S, and P is a probability function defined on this collection of subsets of S. So together this is called a probability space. Now I am going to introduce the concept of random variable on a probability space, and we will see why this concept is important. A random variable on a probability space is a real valued function on S. So those of you who believe all of you had studied functions at your 11th or 12th level. So here a function has two parts, a domain and a codomain or range. So in this case, the domain of the function is S, and it is mapped into R. So for every point in S, there is the image xw is a real number. So x is a mapping from here. It is a mapping from A. So let me put it this way. This is a mapping from S to insert equation. This is the notation we are more used to R. That is for W in S, XW is a real number. So that is what I mean. Okay. So random variable is a real valued function on the sample space. So it will assign to every outcome. So elements of S are the outcomes of the random experiment. So a random variable will assign real numbers to outcomes of the random experiment, and it satisfies some condition that is mentioned over here, but you may ignore it as of now. And in fact, if S is countable, I have mentioned that means if either S is finite or even if S is infinite but countable, that means there are as many elements as there are set of natural numbers, then this condition is irrelevant. Then any real valued function we will call a random variable. Now the special condition is needed only when the set S is uncountable, and there are random experiments which have uncountably many outcomes. So there it is needed. In general, you can just think of random variable as a function which is assigning real numbers to the outcomes of a random experiment. So then there is a concept of a simple random variable. So a random variable is said to be simple if it is taking finitely many value with probability 1. Obviously, in the question of simple random variable will arise only when the set is finite. That means when the random experiment has finitely many outcomes, then a function which is assigning numbers to the outcomes of the random experiment will be simple, in the sense that since there are only finitely many outcomes, so it will have only finitely many values assigned to them, or its range will be a finite set. So here are some examples. So suppose x denotes the number of heads in the single toss of a coin. So we know that one of the basic examples of a random experiment is toss of a coin, because there are two outcomes, head and tail, each has a certain probability. And suppose I count the number of heads. If there is a head, it will be 1, and no head tail, then the count will be 0. So x is taking two numbers 0 and 1 corresponding to the number of heads on each side. So therefore here x is a random variable and it's a simple random variable. Why? It is taking only two values. Now suppose the coin is tossed 10 times and then I count the number of heads. Then what will be the values of this count? If all are tail, then x will be 0. If 1 is a head, and then it will be 1, then it can be 2 heads, rest tails, so it will be 2, and all the way all heads, then it can be 10. So in this case x is taking the value 0, 1, 2 up to 10. So here also it is taking finitely many values, so therefore it is a simple random variable. Now comes a slightly more complicated type of random variable, so discrete random variable, which can take infinitely many values but countably many values. So this is something I have again and again said, that in mathematics when we talk a set is either finite or infinite. In infinite there are two types of infinite set. One is a countable, that means as many as there are natural numbers, and the uncountable. So in infinite set which is not countable is uncountable. So here is an example of a discrete random variable that is not simple. So a coin is tossed until the first head occurs. So you know, in this case the sample space or the set of possible outcomes is not finite, because the first toss may be a head, then I may need two tosses, so tail heads, and then it may be two tails, then a head, and on this way I may need hundreds of tails preceding the first head, and it is not possible to say with certainty that after so many head tosses I will surely get a head. So therefore this is an infinite set. And now if I count the number of tails preceding the head in each case, in the first case there is no tail, so 0. In the second case it is tail head, so 1 tail 1. So tail head there is 2, and so on. So in this case when there are n tails preceding the first head, then it is n. And also you see here, if we count the number of tails, it can be 0, 1, 2. You cannot say that there is some last value of x. So this is an infinite set. So here the random variable is taking all the non-negative integer values. So we call it a discrete random variable. Is it a simple random variable? No, because it is not taking finitely many values. So by discrete random variable I mean either a simple random variable or a random variable that takes countably many values. A simple random variable is always a discrete random variable, but a discrete random variable need not be simple. Here is the example. To be simple, it has to take finitely many values. Now there is a third type of random variable which is called a continuous random variable. So this is a random variable which will take this is a very peculiar case on when you look at it look at this definition for the first time. It is saying that it is taking probability x equal to y with 0 for every real number y. So it is assigning every value 0 probability. And now we will see that this is clearly not possible if S underlying set S of possible set of possible outcomes or the sample space is countable. Then such a random variable does not exist, because that will then violate the second axiom that P of S is 1. So if S is countable and probability x equal to y is 0 for every y, then P of S is equal to 1. That will be violated. But we will see that when S is uncountable, then this can happen. So when S is uncountable, it can happen that probability x is equal to y is 0 for every y, but probability x between two numbers a and b, that has a positive probability. So anyway, that we will see in the next slide. But as of now, let us learn that a random variable I say continuous when it is probability x equal to y is 0 for every number y. Now those of you who would have done some advanced math, you can probably relate this concept to the concept of length. So you know that if I give you a piece of wire, you can measure the length. Similarly in maths there is a concept of an interval. So for an interval the length is an interval is a uncountable set which contains all the numbers between 2 points a and b. So if you include a and b, it's called closed. If one of them is included, then it is semi-open. If both are excluded, then it is called open. So you consider all the numbers between a and b except a and b, then it is an open interval. So in either case the length is said to be b minus a. But then we can prove that length of, if you give me any point set, so length of a a set containing only the number 1 or 0.5 or -1 or 100, length of a set containing only one number is 0. So you see, in case of length, it is possible that each and every point set has length 0, singleton set has length 0, but the length of an interval is positive. So it is, although at the first sight this definition looks a bit strange, but in mathematics it does happen. Now, so we have seen the random variable and three types of random variables. So simple, discrete and continuous. And now we will look at some common features of a random variable. So next what we can want is the probability distribution or the distribution function of a random variable. So x is a let x be a random variable on a probability space. That means x is a real valued function on S. And so if x is continuous, then probability x equal to y is 0. Then if x is discrete, then this cannot be 0 for every y. For some value of y it is 0. So in general, suppose we are interested to know this. Let me get rid of this. So suppose I want to know that what is probability x between a and b, or where a and b are two numbers. So let me also get rid of all this, okay, because this note was written for my math students, MSc math students. So Borel sets and all that, let me not complicate you with all this. So let me also delete with this. So now my goal is very simple, that given a random variable, I want to compute the probability that it is between two numbers a and b. So a less than b. So that is my goal. And now these if I am able to compute this probability for each and every a and b, then that is what I will call the probability distribution of x. Now in order to compute these probabilities, it is enough to define and compute this probability, that fy, where fy denotes the probability x less than equal to y. So this is called the distribution function of x, and it is a matter of just using the finite additive property of probability. So in fact I have left it as an exercise for you to verify that in that case this probability that x is between a and b is equal to fb minus fa. So that is an exercise for you. Hints is given that it is recall property 2. So let me write here the finite additive property. So you see, when we want to compute probability that x is taking values between 2 points a and b, then we can compute it based on the distribution function, which is probability x less than equal to y. So for any probability random variable, the next thing that we want to know is what is its distribution function. So when I talk about the probability distribution of a random variable, I refer to this distribution function only. So now this distribution function has some common properties that I have mentioned, that see that this distribution function is a probability, so it is between 0 and 1, and the other properties require some proof that f is non-decreasing. So these proofs we will discuss in the next class. And now I have another definition of a continuous random variable. So a random variable is said to be continuous if this distribution function is a continuous function. So next, I am ending my lecture today. In the next class, what I will show you, that if the random variable is discrete, that is, it is taking finitely many values with positive probability, with the probability 1, then this distribution function will have discontinuities. And if it is a continuous random variable, that is probability x equal to y is 0 for all y, then this function is continuous. So we actually can classify the random variable as discrete or continuous based on whether the distribution function is continuous or not. Okay, so the distribution function is everything that you need to know about the probability distribution of x because of this relation. So in the next class, I will talk more about the distribution functions. of the random variable, and when we will introduce